I called this week Sean is a big fat liar week, and you'll probably see what I mean as we kind of work through these introductory slides here. The topic we're going to be discussing is something called chemical equilibrium, obviously. So the first thing we got to talk about is what the heck is this idea of equilibrium? And I have to tell you exactly what it's not. So, in these little pictures right here, and these teeny tiny little words that are kind of tough to read on this presentation, but is available as one of the lecture supplements for this week, what we see is this reaction where this N2O4 gas is going to become N2 gas, right? Two different units of that thing. So, this is an example of a decomposition reaction. Well, up to this point in the term, I pretty much showed you these reactions with an arrow going a really particular way, and we just always assumed that it went towards the product. It turns out I'm a big fat liar, and the reason that I'm often lying to you is this concept of equilibrium, right? It turns out that, if we were to actually do this reaction, which is a really great demo that I do for you in lab, as you see this nice colorless gas, which N2O4 is, and then as we started to have the reaction happen, eventually it would start to have a little bit of the product form, which is kind of a brown, orange-brown gas, which warns you that you definitely don't want it in your pants. Anything colored orange is orange for a reason, and we've evolved to avoid things that are orange, so this is a really toxic thing. But anyway, this particular thing, right, would appear to kind of stall out in a certain sense, right? It would kind of look like the reaction didn't go all the way to the beautiful orange gas that NO2 is, and a lot of people would get a little bit confused by that all of a sudden this reaction that I said went towards products kind of stopped. Well, it turns out that it didn't actually stop. What's actually happening is that there is a very appreciable reverse reaction. In other words, this reaction for N2O4 becoming NO2, right? Sure, that's a reaction that happens if you've filled something with a whole bunch of N2O4. But the problem is that there is also the reverse happening as well, where two of these NO2s are coming together to form N2O4. What ends up happening is that we have a reaction that is said to be at equilibrium, where the rate of the forward reaction equals the rate of the reverse reaction, right? And so there's an important definition there. So this idea of chemical equilibrium occurs when a reaction and its reverse reaction proceed at exactly the same rate. Notice what I did not say. I did not say that it's this perfectly balanced thing, right? I did not say that we won't form a whole bunch of products before this chemical equilibrium establishes. I didn't say that that we stay at this perfect, 50-50 mix. That's not what equilibrium is, and that's the most common misconception among students, is just because chemical equilibrium is happening and that the reverse reaction proceeds at the same rate as the forward reaction, it can actually be the case that chemical equilibrium is far towards products, right? And so that would be a perfect example of something up to this point that I would show to you as a reaction, right? Because I knew that I wanted to show you a reaction that went most of the way towards products before it kind of stalled out. And there are many reactions like that that don't stall out at all. They really do go all the way towards products. But many, many reactions have this idea of having an appreciable reverse reaction. So a couple different ways that we can look at this. All of them get a little bit confusing. I'm not going to talk too much about the rate equations here that you see. We may talk about this eventually, but I've found that it's not easy for people to kind of understand what's going on, other than the fact that you can see that there is this kind of like equilibrium state where you can see that there's a little bit more product than there is reactant remaining, right? And so that's kind of important. It's probably easier to kind of think about as you look at the point of view of the reactant, right? And so we see that reactant, that as it reacts, it kind of goes down, 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 and eventually it just kind of levels out. And where we see this leveling out is where we see the forward and reverse reactions actually happening at the exact same rate. But to our eyes, right, it kind of looks like nothing is happening, but that is 100% wrong, right? There's a whole bunch of stuff happening. It's just that there's no net change because the second of one of these turns into two of those come together and form one of these. So we'll kind of develop this theme as we go here. So keep in mind, we've got both forward and reverse reactions occurring. Equilibrium is that special point where the forward and the reverse reaction occur at the same rate. And even though there's a whole bunch of stuff going on at that equilibrium point, that is where we're going to see reactant and product concentration remain the same. So one slide that may or may not be helpful is this one. I know it's got a lot of numbers, but let me just kind of guide you through it. It's essentially saying that no matter where you start along this curve, so it doesn't matter in an equilibrium reaction where you start, right? It must be true that you approach this point regardless of how you get there, right? So I could have started with a whole bunch of N2O4 and no NO2, or I could have started kind of part way, and no matter what happened, due to the kind of the inherent nature of this process, it would go to a certain point and stall out. Always reminded me of kind of the approaching the asymptote in like math class and stuff like that. This wouldn't be a chemistry class without me somehow talking about something that we can calculate, some esoteric thing that you have to calculate. And that is something that is called the equilibrium constant. All this is, by the way, it's abbreviated as a K with a little tiny EQ next to it. Sometimes it's just a K. By the way, that K comes from the word constant in German, right, which begins with a K, friggender. And we're going to talk about a whole bunch of different Ks, really, but all of them are this thing called an equilibrium constant. And so bear with me here. I'll show you kind of like the generalized way of looking at this. All right, so let's pretend that we have this general reaction right here. The equilibrium constant has a really particular look, right? And so what you'll notice about the equilibrium constant expression here, by the way, that is a K sub C, right? That's the equilibrium constant in terms of concentration. That's what that C stands for. What you notice is that it's always products over reactants, right? And so these bars right here, those always are indicative of concentration in chemistry, right? And so what it's saying is that that equilibrium expression is the concentration of D raised to whatever the coefficient is out here, right? That's that little small d, times the concentration of whatever E is raised to its coefficient over the product of the concentration of A to its A power and B to its B power, right? And so that is a K sub C. It turns out that in terms of gases, we can also do the exact same thing. It's just that there can be all in terms of partial pressures, but you'll notice that the K sub P, or in other words, equilibrium constant in terms of pressure, has the exact same kind of structure, right? And so this kind of products over reactants where the coefficients are raised to the exponents are the coefficients in the balanced chemical reaction is going to be important for a whole bunch of different things. So I just wanted to include one slide that kind of shows a real life process, right, which is the Haber process, which is probably one of the most important developments of the late 18th and 19th century. Consumes probably, a ridiculous amount of the world's energy because ammonia is so incredibly important for a whole bunch of different things. If you take a look at the K sub C for this thing, you'll notice that it's the products, right? In this case, it's just ammonia raised to 2 because there is a coefficient of 2 right there. And then you put the reactants on the bottom and raise them, N2 to the first power because there is an assumed 1 there, and H2 to the third power, right, which is assumed there. By the way, these concentrations are measured in molarity. So if we ever get to the point, which we probably will where we calculate Ks, I'll give you the equilibrium molarity of a bunch of these different things. So even though the calculation of K is a huge pain in the butt, quite honestly, it has a whole bunch of information. So I wanted to spend just a second talking about why we should care about K and what it really tells us. Well, the first thing that it tells us is that if it's much greater than 1, right? And by the way, the magnitude of K runs, like from 1 times 10 to like, negative 25 to times 10 to the 50th, right? It's like a huge range. So when I say that K has to be big for this to be true, I'm talking usually about like a 10 to the third, right? So like 1,000 or greater magnitude. If it's really, really big, essentially you have almost all products, right? And so if you have a much, much greater than one, you say equilibrium lies to the right, or you might say equilibrium lies towards products, right? And so the size of this box here, you'll notice that just kind of quickly looking at the measure of K gives you a pretty good idea of, are you talking about an equilibrium reaction? Or are you really talking about something that's almost always, it's almost all to the forward direction, right? So something like this, if K was, let's say 10 to the 10 or something like that, these little equilibrium arrows, by the way, anytime you have some reverse arrow and a forward arrow, that's an indication of equilibrium. Really, you wouldn't need any of that reverse arrow, right? It could just be one of the arrows that we've seen 1,000 times in the first term and a half here, all going towards products. Similarly, if it's the other way around, if you've got a K that's like 0.0001, like 10 to the negative third, or I guess that would be 0.001, but whatever, right? You get the idea. If you're much less than one, and you're just a little bit, by the way, still positive, but just a tiny, tiny number, you're really saying that it's really not accurate to have these arrows, right? If it's really, really small, we might as well just say the reaction doesn't happen as written, right? In fact, if you tried to do this reaction and you had some products, it would actually probably go more towards reactants, right? So obviously there's all kinds of different Ks that we're going to see in a couple of these slides. But I did want to mention a couple of kind of, again, like esoteric things about these K calculations. So there are a couple of kind of bizarro things about calculating or setting up equilibrium expressions like this. One of those things is that the only things that matter in terms of the setting up the K sub C or K sub P expression has to do with you finding gases or something that is aqueous, right? It turns out that if you have something in the solid or liquid phase, right? And so like, for instance, this has one product in the solid phase and the reactant in the solid phase. It turns out that the amount of gas is really the only thing that matters. And it's kind of a bizarro thing that'll really not be something we encounter very often. But that's why, we have to like kind of confront this, is that so if you see like this little phase, right, which didn't really matter to us that much before, it does actually matter a whole bunch in these equilibrium expressions. I thought maybe one of these simulations would help us a little bit to understand kind of what's going on in equilibrium, right? And so what I'm going to do here is I'm going to make kind of an extreme situation, right? I'm going to raise the energy of, the potential energy of my starting material, right? Which are going to be these little A particles here. First of all, I have to raise that just a little bit. Don't worry too much about that hill. That has more to do with something called kinetics, which we're probably not going to study. And so what I'm going to do is I'm going to set something up where the KEQ for this process should be pretty high, right? In other words, most of my A's are going to turn into B's, right? And then it turns out in real life, this is something that is going to happen in the case of reactions, right? So let's start the reaction with a whole bunch of A's. And what you can kind of notice is that eventually I kind of set up this equilibrium state. And of course, it's very, very far towards products. But you'll notice that every once in a while, there is some sort of reverse reaction that occurs, right? And so this is what I mean by equilibrium being a dynamic equilibrium, right? So even though if I had a whole bunch of different particles in here, really nothing would be changing to our eyes, there is actually quite a bit going on, all having to do with this kind of reaction. And of course, this is a simple one where kind of one sphere becomes another colored sphere, but you can imagine that this situation gets pretty complex. So what are some different things you could do? Well, you could heat this sucker up, right? And so when you heat this sucker up, you're not really, in this case, going to affect the position of equilibrium. You're just going to kind of speed up both reactions equally, right? And so I really like some of these demonstrations just because it really helps us to think about it. Unfortunately, I can't quite fit this in here, but so you can imagine that these numbers don't really change that much, right? So the idea of equilibrium is what we're observing are like huge number of particles, right? And so we're not going to see this what kind of looks like, oh my God, it's a 5 and 5. Now it's a 4 and 6, and now it's a 3 and 7, right? It's going to pretty much remain pretty close to the same kind of value of like 2 and 8 or 1 and 9. So hopefully this kind of helps you to think about what's really going on with chemical equilibrium. And of course, I could make the situation where KEQ is really, really, really tiny, which would be the exact opposite, right? And so you can see no matter where I start, eventually we're going to kind of equilibrate where there's a whole bunch more A over there. And of course, we've still got a rate in the forward direction. But hopefully that'll help you think about it. So there are a couple of manipulations of these values of K that we're probably going to investigate more on Wednesday, but I at least wanted to give you some of the rules now so you can start to think about them. So the first one has to do with if I were to take some sort of reaction, there's that reaction that we introduced in the beginning here, right? And then I gave you some information about Kc, right? Well, there's the equilibrium constant expression, which involves the products over the reactants, right? Where everything's raised to their coefficient power. And then I said, hey, it's 0.212, but then I suddenly reversed the reaction on you and I said, okay, what's the K of that? Well, it turns out, as you can see here, what you do is you take the reciprocal of that value. So in other words, you would take 0.212 and you would flip it, right? And so if you did that on your calculator, which by the way, when you take the reciprocal of something, as we'll soon see on Wednesday, you take it to the -1 power if you don't remember that from math class. So that's what you can do if you want to reverse a reaction. Turns out there's other similar rules for, let's say, that I needed for some reason to double the amount of all of my coefficients. Well, it turns out it's pretty simple. All you do is you take that original Kc, and if you multiply everything through by 2, that means you take everything to the next exponent, right? So in other words, we're going to square everything. So that's something that you'll see happen occasionally, right? And so if I wanted to double this, I'd have to square this entire thing, which leads me to that expression right there. So just one other one that may or may not become important on Wednesday that I'll mention. Turns out if you kind of add two reactions together, which is probably the easiest thing to see with an example in a second here, you multiply the equilibrium constants together. So just in case we start to do some of these types of calculations, which is called a Hess's law type calculation, you'll notice that if I give you equilibrium numbers for two different reactions, you can actually add them together. And if you add these two things together, you will actually have to multiply those coefficients together in order to end up with the new KEQ. So those are a couple of things that we should keep in mind, and I will talk to you guys again on Wednesday.